Alright, in this video I'm going to model this problem in ANSYS. As you see here, we have a frame which has two members, member ABC, which is like a beam. It has a force acting at point B. We have one force at A going down 350 newtons, and then we have support at C. We have member BD, which is like a truss member, a link element, because that's gonna carry only forces along its line of action, along the line BD. So we're gonna model this and find forces, force in member BD and reaction forces at point C. Manually this has been done, this problem, and FBD is gonna be 1750 at at C. Reaction at X direction, in X direction is gonna be 1400 Newton, and in Y direction is gonna be 700. So let's have this done in ANSYS. Okay, so we go here, have to make sure it's a structural analysis. Element type, since we are going to use two types of elements, link element, I'm going to add that to my active elements, and then another one is the beam element I'm going to use. Alright, so type 1 is going to be the link one, and then the second one is going to be the beam element. Alright, so then real constant. For the link element, we need to define cross-section area. Since we are not interested in the stresses here, the cross-section area could be anything. So let's say I'm gonna use the millimeter squared as my unit system. So let's say my cross-section area is 10 millimeters squared. So then I close that. Alright, then material property, again, this is not gonna affect our results, but let's say we have a steel, so I'm gonna go here and put 200 megapascal, so 200,000 as my modulus of elasticity. Then I close it. Alright, and then for sections, for the beam we need to define section 2. So I'm gonna consider same cross-section area for my beams. So I consider 10. So let's here for the link, so let's say here width is 3.3 and then height is 3.333. That's gonna make our cross-section area 10. Then let's go and model it. So go key point, inactive. Yes, I'm gonna start from point 0, 0, 0. Let's say that is representing my point A. So that's my point A. Point B, let's look at it, 100 millimeter to the right, 100 millimeter to the right, and then we have point 3, let me see, that was 50 millimeter. Okay, so it has 0.23, and then point 4 is going to be point D, 75 millimeter under that point. So number 4, X is this, but this one is negative 75, the Y. So we have all our key points. Now let's create lines. So I go close this. I want to create lines connecting the key points to each other. 1, 2, 2, 3, and no, I'm sorry, 4 to 2. I have connected this red line. I have to eliminate that. It's not what I wanted, so go delete lines only. Okay, I delete the line. The key points are gonna stay there. Alright, so this is the geometry. Now let's go for meshing. Mesh attributes, we have to decide first. So pick lines. This line and this line are gonna be meshed with our element number 2, which is beam element. Real constant is 1, so material number 1, so this one is right. And for this guy, I'm gonna mesh it with the other type of element we have, which is our link element. So I go there, pick that, and then for sizing, I wanna, yeah, so all lines, I wanna just do one element for each. Alright, so we did that. Okay, and then now we mesh all the lines. Now we can go here and see the list of our elements to make sure that we have them right. Alright, so see, we have 3 elements total. 2 of them are beam element. The third one, which is my link element. Alright, so we have it right. And then now next we have to apply loads. Alright, so apply a load to this point. This was point A. The force was going, oh I'm sorry, we have to apply a force, not displacement. So force on key point, this guy, and then the force is in Y direction. Let's look at the magnitude, 350 going down, so it's going to be negative 350 newtons. So here's the force. I made 2 of them by mistake, so let me eliminate this one. So let's go up, the force, okay, so delete, structural, and the key point, this one, I'm going to eliminate that. No, it's like, it's not displacement, it's force. So I have to eliminate this force here. Alright, that was by mistake. So now go back and apply boundary condition. Okay, so at this key point, this one, we had a pin support. So a pin support is not gonna let X and Y move. And also Z, X, Y, Z. Rotation about X and Y are 0, 2, but the only thing I have here available, rotation is about Z axis. We should set that to be free. So Z, other than that, rotation about Z, everything is closed. Alright, same thing here. Do same thing here. Alright, so do that. Alright, so now we should be ready to run. Let's run the model. Okay, solution is done. Now let's look at the solution. Okay, first we can look at the result, the deformed shape. Yeah, this is how it's going to deform. And let's look at reaction forces, which is something we have in our, we have the solution there. Okay, so it says at node 3 was, this was node 1, node 2, node 3 was, it says reaction at that point, at point C, is going to be 1400 going to the left or negative, and then 700 going down. So does that agree? Yes, it agrees with our ANSYS. Negative 1400 left, 700 down. Okay. Moments are 0, all of them. Okay, and what else? Okay, so at node 4 was here, this guy. Node 4, we have 1400 and 1050. If you find resultant of these two, is gonna be the answer we have here, 1750. But we can look at the forces inside elements. That's not going to be available for the beam element, but for the link element this is going to be available. So let me go here, element solution, then you go down, you see element result, you can do it there. As you see, it says that for the beam elements this command is not available, but for the link element we have internal force given to us here. You see element 1 and element 2, this command has no use, but element number 3, which is our link element, the force is negative 1750. This is what I have here, negative 1750. See the solution manual, or the handwork says 1750 compression, so it's going to be negative. This is what we got here. And then if you're interested in stress, basically ANSYS has divided this force by the cross-section area, and this is our stress. Alright, so that's matching our work, matching the hand calculation. So if you want to see nodal displacement, you can do that too. So you go nodal solution displacement, is going to show us how much each node is going to move. You see node 1, which was where the point of where that force A was, where the point A was. You see it's going to move this much in x direction. These are in millimeter. That's kind of negligible, 0.03 millimeter to the right, and it's gonna go 67 millimeters down, and in z direction no movement. And then point 2 is gonna move too. Point 2 was here, this guy, where the link element and beam elements are connected. So that's one, we have it. The other ones are 0 because we constrained them. So alright, so this shows us how we could model, a frame that has both link element and beam elements. And we found reactions, we were able to find forces and also stresses. Alright, so by the way, if you want to see animation, let me show you. You can go to result viewer here, and then see degrees of freedom, displace the structure. Yeah, you can see the deformed shape, and make animation. See what? Oh, I'm sorry. Yeah, you see it's now it's moving slowly. But if you wanna increase the, no, not this one. If I wanna increase the rate, make it faster. It's making it slower. This is making it faster. So this is how it moves. Yeah. So see, technically, with this frame, this part is moving the most. The other parts are kind of rigid. Alright, so I hope you find it useful.